So, hello everyone, thank you for listening. I'm here to talk about my thesis that I'm about to defend on pulsed plasma thrusters for micropropulsion. And my supervisors have been Mario Merino and Jaume Navarro Caballé, and I've been working as a member of the Plasma and Space Propulsion team at the Universidad Carlos III de Madrid. So the thesis involved the design, development, and experimental characterization of the thruster, in particular a PPT, as I've introduced, but also the design and applied results of innovative experimental diagnostic techniques for the time-varying 3D reconstruction of the exhaust to plasma exhaust of unsteady electric propulsion systems based on electrostatic probes working in the ion saturation regime. Then I'm going to motivate this work by presenting some context and also describing the research questions. Then I'm gonna present the research questions leading to the definition of the thesis objectives and sub-objectives, and I'm gonna use this to introduce the two innovative diagnostics techniques that before I mentioned and that constitute the main contribution of this thesis to the field. These ones involved two diagnostic techniques. The first one is named time series time of flight, and the second one is the waves technique to scan the plume cross section. And to note extend in excess the time of this talk, I'll just leave at the end of the presentations some slides about the second techniques, the second of these techniques that corresponds to our last work, to get a comprehensive description of the plume cross section with significant time savings in comparison to comparable methods in the literature. Now let's start by introducing some context, starting by presenting what EP is. A field with more than 50 years of experience on research and exploration of these technologies that involve the electric and or magnetic fields for accelerating a propellant, for ionizing and accelerating a propellant up to its ejection, and as a consequence to generate thrust. There are different types of electric propulsion systems. In comparison to chemical propulsion, you can get exhaust velocities that can be one order of magnitude higher. However, with lower thrust, making electric propulsion ideal for non-impulsive propulsive missions. The most consolidated technologies are the Hall thrusters and the gridded ion thrusters. However, these two technologies are not the suitable ones for all the mission size scales. For example, in missions in which power and size are limited and that requires down scalability for the EP thrusters. The thrusters of interest are those with a simple structure and or pulsed operation. Indeed, there is an important market niche of interest on providing micropropulsion alternatives for onboard propulsion as the primary propulsion systems for nanosatellites. And even though that these the micropropulsion could also serve for secondary propulsive missions, there is an important market target on these very limited powers and size satellites, as there is an exponential growing trend for these satellites, but most of them basically lack of onboard propulsion, and which would significantly increase their lifetime, especially in the orbits in which they operate, where the non-compensation of drag effects significantly affects their lifetime. And among the two plasma-based alternatives between the former options, we have chosen the pulse plasma thruster for now on PPTs, in particular the evaluative one based on solid propellants, to be the focus of our research, which indeed was the first EP thruster in orbit, and from that point a few dozens of them have been in orbit, and many others have been also qualified. And now we are gonna take advantage of providing an explanation of the working principle to better understand why this is a good alternative for down scalability of a power and size budget. The advantages to make it suitable for miniaturization reside in its simple structure, the absence of an injection system, and also the fact that it operates impulses, which makes them almost independent to the power budget. With this work, we are presenting the first Spanish PPT that is also the first plasma-based thruster for micropropulsion in the country, and also the first time for EP2, so working on pulsed plasmas. So in essence, a PPT consists of two electrodes that extend actually forming a discharge channel, and at one end of them there is a solid propellant clamped between them, and also they are connected to an storage unit, typically a capacitor bank, that also biases them up to a voltage that is sufficiently high, to a high voltage that is sufficiently high for once the discharge is triggered, favoring a flashover along the propellant surface, which will ablate part of it and will ionize it. And these electric currents generating as a consequence of it, that are indeed quite high in the order of a kiloamperes, interacts with a self-induced magnetic field, generating a body force that accelerates the plasma down the channel up to its ejection. So to talk about some order of magnitudes, we have 1 kilovolt for the discharge initial voltage for 1 centimeter height channel, and several centimeters for the electrode length. With these we get several hundreds of specific seconds of a specific impulse, in the order of 10 micronewtons seconds for the impulse speed. Nonetheless, these advantages also deal with several engineering and scientific challenges. For example, the low efficiencies reported so far, and that could be related to with the identification of several ion populations in the PPT plumes. And now we're in situation to define the thesis objectives to justify the sci-tech approach of this research. Hence, we wanted to focus on the plume plasmas, getting a better understanding of PPT plumes, but also to provide the community with innovative diagnostics techniques that improve the existing one in the literature, helping on the former objective, and also that could be applicable to other type of thrusters, especially unsteady ones. But for that, it was of course necessary first to design, develop, and explore in some operational envelope through different diagnostics means of PPT prototype and experimental research platform for which iteration took place. And also from this work, and 5 contributions to international conference have been derived, and also 2 journal publications on Q1, one of each describing the two innovative experimental techniques with which we are contributing the field. In addition, and let's open a parenthesis for that, there are other side contributors to this thesis that even though it took time and not the main focus of this, this is why I'm not going to focus on that today, but they mostly involved the development of a 3-fluid model for planar PPTs, the building blocks for future research, but also the research that I carried out during my research stay at JAXA on easier gridded ion thrusters that also end up becoming a Q1 journal publication. And now let's come back to the two pillars of this thesis in such a way that we can define the sub-objectives of the second one to understand which are the limitations that field faces with all the proposals that we offer and how we address successfully address those problems. To better understand the problem studied, let's just keep in mind about the thruster operation that the electrical discharge of the batteries involve work in the underdamped regime for this capacitance regime in which we work which is basically constrained by the size limitations of this operational range. The natural frequency of that, it's in the order of several hundreds of kilohertz, and also the discharge time is of several tens of microseconds, with the main part happening along the few first microseconds. Then let's address the plume study sub-objectives identification. Studied the plume plasma is useful not just for getting a better understanding of the plume physics of discharge physics, but also to help improve thruster performance, and also to help on some engineering problems as the spacecraft plume interaction. So our research questions to address focused on the two aspects that have been identified on the literature of NSTD-P, and it is basically the most extensive diagnostics methodology for ion speed calculation is to apply traditional time of flight, which has limited physical insight, but also limited applicability in terms of the uncertainty you get if these results are extrapolated to get performance metrics. And also the second thing identifies that concerning the plume divergence studies, they are scarce and there are limited time resolved data, and also the studies found are setup intensive and time consuming. So these are the elements that we identify to try to improve with our proposed techniques. As a consequence, three are the sub-objectives of these main contribution. The second pillar, that is basically the first one is developing a traditional time of flight to provide the framework in order to make comparisons, and two innovative techniques. The first one directly reinterprets the traditional time of flight by considering the entire time series data, proposing an expansion, a model for the expansion of the different ion population that allows for the isolation, and the other one focuses on the cross-section reconstruction by significantly reducing the testing time. But before entering details of them, let's explain a basic thing about a typical plasma measurements with an electrostatic probes working in the ion saturation regime. And for that, we will take an example of a Lammo probe. So having these, we have to see that the light lines represent individual shots, and while the thick one involves the mean. So repetition in this kind of thrusters, repetitions of fires, it's important to get statistical significance. And also we can see how there are different bumps in times that we hypothesize to correspond to different ion populations. Hence, considering a typical time-of-flight techniques with a series of Lamé props distributed along the thruster axis, it's straightforward to compute the ion velocity. But also, as far as we know, we were also the first one getting a first estimate of the plume expansion rate from that. The problem of these approaches is that first, we are not this methodology inherently disregards the fact like each bump, it's also there are contributions to each one of the bumps by several ion population that can have nothing to do to each other in terms of their characterizing parameters, and also that for the plume expansion, even though that we have inferred that by the current decrease from one prop to the next one, this change in the current, it's not just due to the divergence, but also of the thermal spread. So the thermal spread applies much more on the action expansion of the exhaust, while the divergence applies on the lateral one. So the time series technique successfully addresses those limitations by providing an expansion model based on Maxwellian ion distribution that allow for the isolation of each one of the ion constituents, and that allows for the characterization with several parameters. And in the case of the waves technique, we propose a diagnostic physical system formed by an array of wire electrostatic probes to scan the plume cross section, and also to reconstruction to resolve the imposed problem, an algorithm to reconstruct the current density distribution based on variable separation. And this approach involves several time savings up to a factor of almost 8 compared to the existing methods in the literature. So note that with the time series time-of-flight technique, with the same data, we are providing more information than comparable methods, and also with the waves technique, we are also straightforwarding the data acquisition of plume divergence data, time-resolved plume divergence data. And also the second technique, it's applicable to steady thruster. It resolves the plume cross section at each time step. These two works are standalone works, but the results can complement each other in such a way that we get a more comprehensive description of the whole plume physics. In these slides, there are the corresponding representative results of the two novel proposed techniques. In the first case, we have the isolation of the different ion population by applying the time series time-of-flight methodology, in which we can see different ion population distributions characterized by their own mean speed, thermal spread, creation on time and space location, and a divergence parameter, and also a magnitude. and for a specific charge mass radius. So in the case of the WASP technique for the cross-section reconstruction, what we have here on the right is the probe array scan that you use to survey the plume cross-section that is composed by a series of probes, wire probes that are aligned to the two cross sections, and that are in the same case that with the data obtained for the previous techniques, the probes are working in the ion saturation regime. So from these integral measurements with the reconstructions algorithm that we proposed, our tomographic approach, one can resolve the inverse problem and to obtain the local distribution of the current and density at each time step. And the difference with respect to standard radon transform methods is that with this approach we can just simply resolve the problem by separating variables. We have proposed two approaches for this algorithm, one in which we solve it with an exact solution, and a generalized one that could be more practical for some realistic setups and their particularities. So we can see here how is the time evolution of the distribution, in which we can see how the different ion constituents evolve with time, but also with space. We can identify space asymmetries and also a different expansion with the two cross directions, in which we can see that the plume spreads more along the unobstructed plane than the direction perpendicular to the electrons. That this is something characteristic of this kind of rectangular configuration. We also see that it's the first time that it is observed that there are two peak profile along the unobstructed plane, and that there is also deviation towards one of the cathodins in addition to one of the thruster sides. It could be also related to manufacturing defects. So to conclude about the thesis of fending, that is concluding about the work carried out and also the findings, and that on the one side that involved the design, development and experimental characterization of a low power class ablative PPT experimental platform named Pulsar, that has been the first Spanish plasma-based propulsion system, and also the first time for the EPG research group working on pulsed plasmas. And the focus of this experimental characterization in terms of operational parameters has been the under 10 joules discharge energy regime. On the other side, that has been the main contribution of this thesis to the field. It involves the two experimental diagnostics tool for the time resolved 3D reconstruction of a transient exhaust. These two techniques are standalone works, but the results can complement each other to get more comprehensive description of the plume of the whole plume description, as the whole plume physics. Sorry. So these two techniques are based on electrostatic probe measurements working in the ion saturation. These probes working on the ion saturation regime, and these two techniques are fast to implement and cost effective. And they too represent an improvement upon the state of the state-of-the-art comparable analysis, in the sense like they provide more information and faster. And also, as I previously mentioned, they are applicable to other EP, in the case of waves also to steady thrusters, but they are mostly of the interest of unsteady EP. So these two techniques have been implementing of the plume of the developed PPT with serving two purposes. First, to validate them, but also these are found valuable in the findings are valuable in themselves, as and also because they are consistent with the literature, but at the same time they provide new insights. So we have been able to identify the different ion population. We have been able to isolating and then individually characterize them, and also we have been able to assess time resolved plume, the time resolved plume divergence data, enabling the study of asymmetries present in the plume. The main findings among these results is that 3 ion groups are systematically identifying the plumes across different operational cases with ion speeds up to 50 to 70 kilometers per second for the first population, and to around 30 kilometers per second for the second one. Which is typically the one that drives a much more current, the major part of the plume current. And also we have seen how the plume current linearly scales with the discharge energy. As we previously mentioned about the plume section, the plume cross-section characterization, we saved up to a factor of, we have time savings up to a factor of almost 8 with the new techniques than comparable methods in the literature that are typically based on the translation of probes, of local probes. And also we have seen how the plume spreads more along the unobstructed plane, characteristic of this kind of rectangular configuration, and also that there are deviation towards the cathode and one of the channel sides. And also we have seen that while along the perpendicular direction to the electrodes, the profile it's single peaked, it is double peaked along the unobstructed plane, which warrants for the investigation. Further investigation. So we can see here the time evolution of that, in which the conclusions that I've been explained are illustrated over time. So to close this presentation, I'm gonna do a recap of the published and submitted content that basically involves 3 journal papers in Q1 journals, 2 of them regarding the PPT work, and 5 conferences, international conference about the PPT, in additional one, all of them as first author, in addition to other works as co-author, technical reports, tutoring of students, etc. And finally, I'm going to outline some proposed future research lines, PPTs directly derived from the work done along these years, that are fundamented on 4 bases. In the first case, we could we could enhance the engineering level of this prototype, and also to develop the conceptual design of impulsive thrust balance that was carried out as a side contribution of this thesis, but focusing on the more science or sci-tech approaches of this work. The main activities would involve the advancement of the presented techniques, and also the continuation of the modeling and of the modeling basis presented on this in this thesis, as well as the implementation of the numerical solution proposed in the thesis to solve them. Now this presentation is finished. I'll leave some additional material in case it is of the interest of the audience, and I just want to say thank you for listening.